Welcome to the problems on heat exchangers, to the session on heat exchangers. I am going through the next problem, the problem number 6. First I am reading the problem. Steam at atmospheric pressure enters the shell of a surface condenser. Steam is entering to a surface condenser at atmospheric pressure. What is an atmospheric pressure? It is 1 bar. Steam at atmospheric pressure enters the shell of a surface condenser in which the water flows through a bundle of tubes of diameter 25 mm at the rate of 0.05 kg per second. The inlet and outlet temperatures of the water are 15 degrees Celsius and 70 degrees Celsius respectively. The condensation of the steam takes place on the outside surface of the tube. That means what he has given is the water is flowing through the tube which is having 25 mm diameter. Over this tube the steam is flowing and it is at atmospheric pressure. Atmospheric pressure is nothing but 1 bar pressure, and it is condensing. That means it is releasing heat to the water, due to which the temperature of the water is rising from 15 degrees Celsius to 70 degrees Celsius. Since the steam is condensing at atmospheric pressure, as we know, the boiling point of water or the saturation temperature for the water at atmospheric pressure is 100 degrees Celsius, we can assume the inlet and outlet temperature of the steam, that means the hot fluid, as 100 degree Celsius, and he has given the diameter of the tube through which the water is flowing, which is 0.025 meter or 25 mm, and he has given the overall heat transfer coefficient as 230 watt per meter square degree Celsius, and he has given the mass of the water which is flowing through the tube as 0.05 kg per second. Here in this problem he has given all the 4 temperatures. We know the inlet temperature of the cold fluid, outlet temperature of the cold fluid, inlet temperature of the hot fluid, outlet temperature of the hot fluid. The problem can be solved using LMTD method, but in the problem itself he has specified to solve the problem using NTU method. And using NTU method we need to find effectiveness of heat exchanger and length of the tube, and also we need to find out the amount of steam which is condensing over the tube, and he has given the latent heat of steam. Latent heat is nothing but the amount of heat which is to be added or removed to a substance per kg to cause a phase change. Okay, now in this problem he has given all the 4 temperatures, but he asked us to find the effectiveness of the heat exchanger and the length of the heat exchanger using effectiveness method. Effectiveness can be given by the equation. One of the equation for the effectiveness is C suffix C into Tc2 minus Tc1 divided by C minimum into Th1 minus Tc1. We know that when boiling of water takes place, all the heat which is added to the water is utilized to undergo the change of phase, and there is no increase in temperature. Similarly, during condensation of the steam, all the heat which is removed from the substance, from the steam, and it undergoes a phase change without undergoing any change in temperature. That means whatever may be the heat added or whatever may be the heat released, there is no change in temperature. Therefore, the heat capacity of the hot fluid can be considered as C maximum in this case, and the heat capacity of the cold fluid can be considered as minimum as it undergoes the temperature change. Assuming the cold fluid is having minimum heat capacity, the equation for the effectiveness becomes Tc2 minus Tc1 divided by Th1 minus Tc1. Substituting all the four temperatures, we will get the effectiveness. We got effectiveness value. Next, we need to find the length of the heat exchanger. By the equation of NTU, we know that U into A by C minimum, where U value is given and area value, A value can be found out using the equation pi dl. D value is given. If we found the NTU value, then it is possible to find the length of the heat exchanger which is asked in the problem. To find NTU, we are having the equation of effectiveness for parallel and counterflow heat exchanger. But since the hot fluid is having the maximum heat capacity and it is unlimited, whatever may be the heat added at saturation temperature, it is utilized to undergo phase change, and hence the CH or the C maximum, the heat capacity of the hot fluid, is considered to be infinity, and heat capacity of the cold fluid is considered to be C minimum. Any value by infinity we will get 0. That means heat capacity ratio, the value of capacity ratio C, which is defined as the ratio of C minimum by C max, becomes 0. And for irrespective of parallel flow heat exchanger and counterflow heat exchanger, when the C value is 0, the effectiveness equation is given by 1 minus e to the power of minus NTU minus n. Okay, we'll find this equation. You can go through the data and book. The equation is given in the data and book itself for the value C is equal to 0. There is no need to remember these equations. As I said earlier, in heat exchanger problems, in heat transfer problems, there is no need to remember any of the equations. Substituting here the value of effectiveness, we can find the value of NTU, which we got as 1.04. Now substitute this value of N, capital N, NTU value, in the equation of NTU, which is given as UA into C minimum, where U value is known, NTU value is known, the only unknown is L, and we can find out the length of the heat exchanger, which we got as 12 meter. Next, he asks us to find the rate of steam condensation. Here in this problem, the hot fluid is releasing its latent heat to the cold fluid, and the temperature of the cold fluid is rising from Tc1 to Tc2. Therefore, heat absorbed by the cold fluid is equal to the heat released by the hot fluid. Heat released by the hot fluid can be given by mass of hot fluid into latent heat. Latent heat is given in kilojoules per kg. I substituted here in joules per kg because I substituted the specific heat of cold fluid 4187 in joules per kg. Here mass of cold fluid is given, the specific heat of the cold fluid is given, Tc2 is known, Tc1 is known, and latent heat of hot fluid is also known, which is 2257 kilojoules per kg. The only unknown is mass of the hot fluid. We will get mass of the hot fluid as 0.00509 kg per second. This is the amount of steam which is condensing over the condenser per second. This completes this problem. The next problem is a single pass shell and tube heat exchanger. It is a shell and tube heat exchanger consisting of 100 tubes. It is a single pass, but it consists of 100 tubes. Single pass is nothing but the flow of fluid from one direction to the another direction. It may be left to right or right to left. It doesn't take any turns. That is called single pass. Okay, a single pass shell and tube heat exchanger consisting of 100 tubes. It is a single pass heat exchanger but consisting of 100 tubes, and the tube is having, it is a concentric tube having inner diameter 25 mm through which one fluid is flowing, and it is having an outer diameter of 29 mm. It is a concentric tube. The inner tube is 25 mm and the outer tube is 29 mm is used, and this heat exchanger is used for heating 500 kg per minute of water from 30 degrees Celsius to 70 degrees Celsius. That means he has given the mass flow rate of cold fluid in kg per minute. Tc1 value, the inlet temperature of the cold fluid is 30 degrees Celsius. Tc2, the outlet temperature of the cold fluid is 70 degrees Celsius. With the help of steam condensing at atmospheric pressure on the shell side. Here also the steam is condensing similar to the last problem, and it is condensing at atmospheric pressure. That means we can take the inlet temperature of the hot fluid and outlet temperature of the hot fluid is 100 degrees Celsius. It remains same, and the steam is flowing through the outer shell. He has given steam condensing at atmospheric pressure on the shell side. Shell side is nothing but outer tube, and the water is flowing through inner tube of diameter 25 mm. Calculate the overall heat transfer coefficient based on inner area and length of the tube bundles. He asks us to find overall heat transfer coefficient U based on inner area and length of the tube bundle, and we need to find what is the length of the heat exchanger. If the condensing side heat transfer coefficient is 5000 watt per meter square degree Celsius, condensing side means here the steam is flowing through the shell and the water is flowing through the tube, inner tube. He has given the value of H0 because the steam is flowing through the outer tube. He has not given the value of Hi, means water side is not given. Heat transfer coefficient of the water is not given. Heat transfer coefficient of steam is given, which is 5000 watt per meter square degree Celsius, and he has given take the fouling factor on the water side to be 0.0002 meter square degree Celsius per watt. See, what happens is when the water is flowing through the tubes of heat exchanger, the impure particles which are present in the water adhere to the inner surfaces of the tubes. and it forms scaling on the inner surfaces of the tubes. These impure particles which are adhered to the inner surfaces of the tubes on the inner surfaces of the tubes offers resistance for the flow of heat between the two fluids, and the resistance offered by these impure particles which are adhered to the inner surfaces of the tubes is called fouling factor. What is fouling factor? It is the resistance offered by the impure particles which are present in the water. When they adhere to the inner surfaces of the tubes, they offer resistance to the flow of heat, and the resistance offered by these impure particles is called fouling factor. On the water side he has given, that means RFI he has given. On the steam side he has not given. The resistance offered by the impure particles on the steam side is not given. On the water side he has given, which is 0.0002 meter square per degree Celsius per watt, and he has given this value for per tube. And he has given neglect the effect of fouling on the shell side. There is no need to consider the fouling factor of shell side, means the steam side, and thermal resistance of the tube wall. And he has given the properties of water at a mean temperature of 50 degrees Celsius. I already said in the last problem itself, if he has given the properties of fluids, it is okay. If he has not given, take the properties of values from data and book at average temperature. Here you can see the water enters at 30 degrees Celsius and leaves at 70 degrees Celsius. The average temperature is 50 degrees Celsius, and he has given the property values for water at 50 degrees Celsius at the mean temperature. If he has not given, you can take these values from the data and book. In the data and book he has given the property values of water and many fluids and atmospheric air. Okay, in this problem he has given directly, there is no need to take. In the problem he has given there are 100 tubes. Inlet diameter of the inner diameter of the tube is 25 mm through which the water is flowing. It is a concentric tube where the inner diameter is 25 mm and outer diameter is 29 mm. The water is flowing through the inner tube and the steam is flowing through the outer concentric tube of 29 mm, and he has given mass of the cold fluid, that is the water, as 500 kg per minute. I converted that into kg per second, which is 8.33 kg per second, and he has given inlet temperature and outlet temperature of both cold fluid and hot fluid, and he has given heat transfer coefficient of steam side, that means the outer tube, which is 5000 watt per meter square degree Celsius, and he has given fouling factor of water side, means inner side, inner tube. I already said the fouling factor is nothing but due to the waste particles which are present in the water adhered to the inner surfaces of the tubes and offers resistance for the flow of heat between the two fluids, called fouling or scaling. Now he asks us to find the overall heat transfer coefficient based on inner area. If you go for data and book, you will find two equations, one by ui equals and one by u naught. But in the problem itself, he has mentioned calculate the overall heat transfer coefficient based on inner area. Therefore, consider the equation 1 by ui equals 1 by hi plus 1 by plus rfi plus ri by k into ln r naught by ri plus ri by r naught into rfo plus ri by r naught into 1 by h naught. H naught value is already given in the problem itself directly. Therefore, we need to consider this equation. But he asks us to neglect. You can see here, he asks us to neglect effect of fouling on the shell side and thermal resistance of the tube wall. Therefore, in these equations, the thermal resistance of the tube wall is given by Ri into K, which we can neglect because thermal resistance he asks us to neglect. We can neglect, and similarly he asks us to neglect the fouling factor on the shell side, that means the outer tube. Therefore, we need to neglect these two equations, and therefore the overall heat transfer coefficient equation becomes 1 by UA equals 1 by HI plus RFI plus RI by R0 into 1 by H0. In these equations, H0 value is directly given in the problem, but we need to find the HI value, which is not given in the problem, and it doesn't ask us to neglect. To find HI, we are having the equation of Nusselt number, which is given by H into D by K. HI into Di by K. But to find Nusselt number, first we need to find Reynolds number, which can be found using the equation rho Vd by mu, or for pipe it can also be found using the equation 4m by pi d mu. Mass of the cold fluid is given because we are finding HI, not H0. And through the inner tube, the water is flowing at a rate of 8.33 kg per second. 4 into m, pi into d. We need to substitute di because we are finding HI. Pi di into mu. And there are 100 tubes. This 8.33 kg per second of water is flowing through the 100 tubes, not a single tube. Therefore, multiplied by 100 tubes, we will get Reynolds number as 7717, which is greater than 2300. Therefore, the flow through the tube is turbulent. For turbulent flow, for a fully developed flow, we are having the Nusselt number equation equals 0.023, general equation Re to the power of 0.8, Prandtl number to the power of 0.33 from data and book. For internal flow, in forced convection, you will get this equation. Substituting the value of Reynolds number and Prandtl number value is given in the book, in the problem itself. We will get Nusselt number. Then substituting this Nusselt number value in the equation of Nusselt number, we can find HI, heat transfer coefficient value of inner side of water. Now we are having the value of HI, H0 and RFI. RFI is nothing but the fouling factor on inner side. We can find the value of UI, overall heat transfer coefficient. Once we find overall heat transfer coefficient, we can find the heat exchange between the cold fluid and the hot fluid. The heat released by the hot fluid is absorbed by the cold fluid, and heat absorbed by the cold fluid can be given by the equation mc into cpc into tc2 minus tc1. And we will get the value equals 1.369 into 10 to the power of 6 watts. This is the amount of heat which is exchanging between the hot fluid and the cold fluid per second. He asks us to find the length of the heat exchanger. By the equation of heat transfer, we are having UA into theta suffix m, where Q is the total amount of heat transfer, U is overall heat transfer coefficient, surface area is given by pi d into L, and we can find the value of L in this equation. Theta m can be found out. LMTD can be found out using this equation TH1 minus TC1 into TH2 minus TC2, considering it as an parallel flow heat exchanger. Q is already found out. U is already found. Surface area is nothing but is given by the equation pi d L. The only unknown here is L, and we can find out the value of L, which is 4.6 meter.